Okay, welcoming you all to another session of current electricity. In today's class, we are going to study about the temperature dependence of resistivity. Temperature dependence of resistivity. Okay, what is the expression for resistivity we have learned in the previous class? Rho is equal to M divided by N is square root. This is the relation for resistivity we have studied in the previous session. What is M? Mass of the electron. What is N? Number density of free charge carriers. What is E? Charge on the electron, charge of the electron. And tau, relaxation time or average time interval between two successive collisions, right? Now let us consider the temperature dependence of resistivity for a conductor. Now, okay, when you see this expression, rho is inversely proportional to N into tau because mass of the electron is independent of temperature. Charge on the electron is also independent of temperature. Now, when I write this, I will exclude N from here. Why? Because for a conductor, the number density of free charge carriers is enormous. Number density of free charge carriers is enormous for a conductor, which means as a result of the increase in temperature, although free charge carriers may come into play, but that won't significantly affect the number density because already it is enormous. Which means the resistivity rho is inversely proportional to relaxation time, that is average time interval between two successive collisions. Now the question I am asking, as temperature increases, what will happen? As temperature increases, what is expected here? As a result of increase in temperature, what will happen? As we have studied earlier, temperature increases means randomness increase. When randomness increases, more and more collisions will take place, which means collision frequency increases. I repeat, as a result of increase in temperature, randomness increases. As a result of the increase in randomness, more collisions will take place, which means collision frequency increases or the average time interval between two successive collisions decreases, which means relaxation time tau decreases. I hope it is clear to you. As a result of increase in temperature, more collisions will take place. Collision frequency increases, which means the average time interval between two successive collisions decrease. So, as temperature increases, tau decreases, which implies the resistivity rho increases. That is the most important thing you have to understand. The resistivity of a conductor, I repeat, resistivity of a conductor increases with increase in temperature. The resistivity of a conductor increases with increase in temperature. This is because with rise in temperature, collision frequency increases or relaxation time decreases. That means the resistivity as a function of temperature can be written as rho is equal to rho 0 into 1 plus alpha into T minus T0. rho as a function of temperature. This is an empirical relation, something that is verified through experiment, and this is an equation applicable for a conductor. The resistivity as a function of temperature is given by rho 0 into 1 plus alpha into T minus T0. What is rho 0? Rho 0 is resistivity at T0 temperature. And what is rho of T? The same, resistivity at the time T. Now, if T is greater than T0, what will happen? If T is greater than T0 implies rho of T must be greater than rho 0. In that case, rho of T must be greater than rho 0, which means alpha is positive for a conductor. Alpha is positive for a conductor. Therefore, we say, what is alpha here? I didn't specify. Alpha is called temperature coefficient of resistivity. Alpha, I repeat, what is alpha? Temperature coefficient of resistivity. That is alpha. That means here alpha is positive for a conductor, which implies a conductor has PTCR. What is the full form of PTCR? Full form of PTCR. Positive temperature coefficient of resistivity. PTCR means positive temperature coefficient of resistivity. That is what I can say for a conductor. In the similar way, the resistance R as a function of temperature for a conductor can be written as R0 into 1 plus alpha into T minus T0. Now you can understand the terms easily. What is R0? A resistance at the temperature T0. What is R of T? A resistance at the temperature T. What is alpha? TCR, which is temperature coefficient of resistivity. Ready? So this is also an empirical formula, understand please. Positive temperature coefficient of resistivity is alpha, for conductor alpha is positive. For a conductor alpha is positive. So if T0 is equal to 0 degrees Celsius, R1 is the resistance at T1 degrees Celsius, R2 resistance at T2 degrees Celsius. Okay, ready? Which means I can write R1 is equal to R0 into 1 plus alpha into T1. Now from here, what will be R0 is equal to? I want you to write by yourself. R2 is equal to, similar way I can write R2 is equal to R0 into 1 plus alpha T2. Ready? That means I will get again R0 is equal to another expression. I want you to write by yourself. Okay. Now which means, okay, let us subtract these two equations. What will be R2 minus R1 here going to be? R2 minus R1. R2 minus R1. So here R0, this is plus R0, this is R0, this is R0. R2 minus R1, just you please calculate. I hope I will get it as R0 into alpha into T2 minus T1. I think this is what I am going to get as R2 minus R1. Now, why I write this equation is because generally you have a tendency to write R2 is equal to R1 into 1 plus alpha into T2 minus T1. This is absolutely wrong, I have to say. Look at that expression. Will you get the same answer here? No way, right? R2 is equal to R1 into 1 plus alpha into T2 minus T1 is wrong to write. Don't write likewise. From here you will get R2 minus R1. I hope I am right in my solution. Because from, okay, R0 is common here. 1 minus 1 is 0. Alpha into T2 minus T1. So R0, okay, I hope I am right here. So I got two expressions here. R0 is R1 divided by 1 plus alpha T1. This is R2 divided by 1 plus alpha T2. Now you can simplify, or you can just equate these two equations and then you can arrive at the conclusion. From here you will arrive at the conclusion for alpha is equal to R2 minus R1 divided by R1 T2 minus R2 T1. This is an equation for alpha, that is temperature coefficient of resistivity. Please understand that here T2 is in degrees Celsius, T1 is in degrees Celsius. Is it okay? In this formula, T1 and T2 you have to take in degrees Celsius, and please understand that this equation is valid if and only if T0 is equal to 0 degrees Celsius. This is applicable only if and only if T0 is 0 degrees Celsius. This equation can be used only in those situations where T0 is equal to 0 degrees Celsius. Ready? I hope this part is clear to you. This is applicable if and only if T0 is equal to 0 degrees Celsius. Okay, please make a note of these ideas, all of you. I hope it is clear to you. Alpha is equal to R2 minus R1 divided by R1 T2 minus R2 T1. I hope it is ready to you. Okay, now we will consider the graphical representation of resistivity. Now let us consider what for a copper. For copper, the graph, the resistivity as a function of temperature, rho versus temperature in Kelvin. As you see in the textbook, the shape of the graph is likewise. This is for copper. Copper is a conductor. Okay. Then I will consider the same for a nichrome wire. Nichrome is a material used for the construction of a standard resistance. Rho versus T, the graph is a straight line for nichrome. This is the shape of the graph for nichrome. Now you can have to understand that for materials like copper, alpha comes out to be variable, right? That's the reason why the graph is curved. Here the graph is a straight line. Now the important one I am going to draw is for a superconductor. For a superconductor, the variation of resistivity to temperature. Up to a certain temperature, say critical temperature, the temperature at which a substance just converts into the superconducting nature. Up to that temperature, the resistivity is 0. So at that particular temperature, the resistivity increases sharply, and the shape of the graph is like this. Now you can see the first and third graph. Beyond the temperature, it behaves like an ordinary conductor, just like the graph for a copper. Below that temperature, the resistivity is 0. That is what you see here. Ready? This is how I can explain for the temperature dependence of resistivity associated with the conducting materials. Now let us consider the same for a semiconductor. For semiconductors, okay, in case of conductor, the charges were free charge carriers. Again I am writing for semiconductors and insulators. Again I have the formula rho is equal to m divided by Ne square tau. Okay, or we can see rho is directly proportional to 1 by n tau. Now unlike a conductor, and why I said unlike a conductor? Because for conductor we took n as a constant, right? Unlike a conductor, we have no freedom to take n as a constant here. Why not? Because in semiconductors and insulators, the charges are bound. Charge carriers are bound charge carriers. Unlike conductor, where there were enormous number of free charge carriers, we cannot get such a thing in case of an insulator or semiconductor. Then what should I say? In case of semiconductor and insulators, with rising temperature, electrons will overcome the attraction force from the nucleus and they will become free. I can say as temperature increases, number density increases, relaxation time decreases. Let me tell you an important point. The increase in number density dominates over the decrease in relaxation time. Because as temperature increases, more and more charge carriers becomes free for conduction. So when it comes to semiconductors and insulators, the increase in number density is more dominant than the decrease in relaxation time. I repeat, the increase in number density is more dominant than the decrease in relaxation time, which implies resistivity. So number density increases, relaxation time decreases. The increase in number density is more dominant than the decrease in relaxation time, which implies rho decreases. The resistivity of insulators and semiconductors decrease with the increase in temperature, which means semiconductors have NTCR. What does NTCR represent? Negative temperature coefficient of resistivity. Negative temperature coefficient of resistivity is therefore semiconductors and insulators. Okay, semiconductors and insulators have a negative temperature coefficient of resistivity, which means with increase in temperature the resistivity decreases. If I plot a graph for resistivity as a function of temperature, this is applicable for a semiconductor. The graph is like this. The graph is like this for a semiconductor. Hope this is clear to you.